explain power factor. To understand the concept of power factor, let's first recall the definition of some basic terms. kW is working power. It is also known as actual power or active power or real power. It is the power that actually powers the equipment and performs the useful work. kVAR is reactive power. It is the power which magnetic equipments like transformer, motor and relay need to produce the magnetizing flux. And kVA is the apparent power. It is basically the vectorial summation of kVAR and kW. Now let's understand power factor with the help of an example. Consider a man dragging a heavy load. In this case, the working power or actual power is in the forward direction, where he actually wants his load to travel and is equal to kW. But practically, he cannot drag his load on the horizontal surface, as doing so will give him a tremendous backache. So his shoulder height adds a little reactive power, that is kVAR. Thus the apparent power which the man is dragging will be the vectorial summation or resultant vector of kVAR and kW, and is called kVA. As we can see, the power triangle illustrates the relationship between kW, kVA, kVAR and power factor. Angle theta of this power triangle graphically indicates the ratio between the working power and the apparent power. Thus, power factor of an AC electrical power system is the ratio between the real power flowing to the load and the apparent power in the circuit. It is a dimensionless number between 0 and 1. We can see that in the power triangle, which is a right triangle, true power forms the adjacent side and apparent power forms the hypotenuse side. Thus, power factor ratio is also equal to the cosine of the phase angle, which is theta. Mathematically, power factor is expressed as. Now let's see, if no power is wasted, then what will be the power factor? For this, let's consider the same example where the man was dragging a load. If the man doesn't have to waste any power along his body weight, then kVAR will be very small and will be approaching to 0, while kW and kVA will be almost equal. And cosine theta will also approach to 1. This implies that the power factor will approach to 1. Now let's understand what will be the power factor in different types of circuits. For a purely resistive circuit, the power factor is 1. Because the reactive power is 0. Therefore, the opposite side of the triangle, which will represent reactive power, will have 0 length. Thus, the power triangle will look like a horizontal line. And for a purely inductive circuit, the power factor is 0. Therefore, the adjacent side of the triangle, which will represent true power, will have 0 length. Thus, the power triangle will look like a vertical line. In a purely capacitive circuit, there are no dissipative or resistive components, so true power will be 0. This makes any power in the circuit purely reactive. Thus, the power triangle for a purely capacitive circuit will be a vertical line pointing downwards. Thus, we can conclude that for different types of circuit, we have different power factors. Note that, in order to have an efficient system, we need a power factor which is nearly close to 1. Related terms are